Sorry, Kamal. We can all stand there.
Okay. Should we get started?
Let's get the sign language person, right? Because we. Well, maybe we should start, right? Because it's already 9:08.
Yeah. Should I go ahead? Okay. Okay, folks. Let's get started. So, welcome to ICML 2019. So I am Kamolika Chaudhary. I'm one of the program chairs, and my co-chair is Ras Salakudinov, and there is Eric Shing, our general chair, is on the stage. Here's our organizing committee. Our workshop chairs are Arthur Greton and Hong Lak Lee. Tutorial chairs are Nina Balkan and Raya Hadsel. Our local chair is Andrea Brown. Diversity chairs are Barbara Engelhardt and John Cunningham. Sponsorship chairs are Eric Southard, Faye Shah. Publication chairs are Shakir Mohammed and Alexandre Bouchard Cote. Press chairs are Catherine Gorman and Jennifer Wortman-Wan. We have expo chairs, Andrew Wilson and Lee Song. And last of all, and most importantly, we have our workflow chairs, Lisa Lee, Devendra Singh, and Paul Liang, who made the whole thing possible. So let's have a big hand for them. Okay. So we had a large program committee this year. So we had, for the first time, ICML had a 3-tier program committee. So we had 36 senior area chairs, 212 area chairs, and 358 reviewers. So this is a first for ICML. So, as you know, the conference has been growing, and, this is the biggest ICML ever so far. We had 3424 papers went through the review. So these were how many papers that got submitted. And we accepted 774 of them with an acceptance rate of 22.6%. You can see the conference itself also has been quite big. So we have 11 tutorials this year and 31 workshops. Submitted and accepted papers. So the conference has been growing for, as you guys have noticed, the conference has been growing for the last several years. Last year, we had about 2,500 submissions. This year, we went up to 3,500. And, the accepted papers have also grown more or less accordingly. Okay? And so these were the top, major subject areas. So this year we divided the subject areas into 8, the entire conference into 8 tracks. The top 2 subject areas are deep learning, but very close to deep learning, we also have general machine learning. So a lot of people are working on general machine learning as well. Then we have reinforcement learning, optimization, trustworthy machine learning, which covers things like privacy, fairness, adversarial examples, security, so on and so forth, applications, theory, and probabilistic inference. Okay, awards.
So this year, I want to say a few things about awards. So first, very important, we have a list of outstanding reviewers. And there is about 170 outstanding reviewers. And those are the people who really, contributed a lot and made this conference be successful. Let's give him a clap. Now, the next award is the Test of Time Award. And it goes to, in suspense, it goes to the following paper that was published at ICML 2009, Online Dictionary Learning for Sparse Coding by Julien Marial, Francis Bach, Jean Pons, and Guillermo Sapiro. So let's give it a big hand. Congratulations. And make sure that you come and listen to the talk on Wednesday. We also have 2 Best Paper Awards. The first one is Challenging Common Assumptions in the Unsupervised Learning of Decent-Angular Representations by Francesco Lacaseta, Stéphane Bouet, Mario Lusic, Gunnar Rach, Sylvie Gelli, Bernard Cholkov, and Oliver Bachin. So let's give these authors a hand. And the second paper is Rates of Convergence of Sparse Variational Gaussian Process Regression by David Bird, Carl Edvard Rasmussen, and Mark van de Wilk. And let's give them a hand as well. So congratulations. This year, we also had a number of fantastic papers. So as program chairs, we've decided to give out the following 7 best honorable mentions. I'm not going to go through all of them, but you will hear about them at the session. So make sure that you come and check these papers out. It's just so many fantastic papers, and the conference is growing. So make sure you come and see those papers. So congratulations again. Now, very quickly, we also have invited talks. The first talk is going to be today. It's going to be given by John Abad from U.S. Census Bureau and Cornell University. And the talk is on U.S. Census Bureau tries to be a good data steward in the 21st century. So it's going to be right after it's talk about the privacy and such. Tomorrow, we're going to have Odi Bilar from EPFL talking about machine learning for robots to think fast. It's going to be very much a robotics-oriented talk. It's very looking forward to that. And then on Thursday, we have Alison Gopnik from UC Berkeley. Is going to be talking about what a 4-year-old can do that AI can't yet. So exciting talks. Now, finally, I just wanted to highlight a couple of quick things. What was new this year at ICML? And there are 2 things that we've introduced. One is the high-risk, high-reward papers. And the second is code submission, optional code submission. So let me say a few words about those. So, sometimes as program chairs, we're thinking about, many times you have papers that are very creative or that are very unorthodox or, trying to solve new or ask new research questions or look at the new research ideas. But again, they could be unorthodox. And sometimes these papers get lost, in the review process. So we designed a special category for papers like these, that particularly looking at creative ideas or explore new research directions. And we're happy to, say that 5% of all the accepted papers basically fell into this category. So make sure you come and check them out. And then finally, this year we've had an optional code submission policy. And at the submission time, so you had an option as an extra supplementary material, you had an option of submitting the code, and reviewers were encouraged to look at the code if they wanted to, clarify a few things. And about 60% of all submitted papers out of 3,400 papers included the code. And what's amazing is about 67% of accepted papers at the camera-ready time had code accompanying basically their paper. So that's a great achievement. And thank you everybody in this audience who contributed to that. And you can read about it in the blog. Now let me pass it to our general chair, Eric Zink, who's going to do the closing remarks.
Thank you. I want to add some more thanks to the grant. First of all, I want to point out that Russ and Carmelita has done an amazing amount of work to put together this conference. You can see we broke record in the number of submissions, in the number of attendees. The logistic challenge, the reviewer burden has been unprecedented. So I want to really represent all of you to thank both chairs for their hard work. Let's give them applause. The conference is also not possible with very, very capable and amazing logistic support from our local chairs and also from actually people you don't see their names on the booklet. I want to name some of them. Andreas Brown, Lee Campbell, and Mary Ellen Perry. I want to particularly thank the three of you who has been constantly supporting us, in planning all the logistics and conference setups back in the stage. And you've given us a huge amount of help in making this conference possible. Thank you very much. And yeah, and well, now it's time for me to represent all the organization committee and also the International Machine Learning Society to welcome all of you to the conference. And before I hand it to the first speaker, I want to remind you there is an email sent out to all the attendees of this conference to vote for the new board members of our Machine Learning Society. Please make sure that you vote before you go home, hopefully. Thank you very much, and welcome to ICML 2019.
Okay, so it is my pleasure to introduce the next speaker, who is our first invited speaker. John Aboud is the US Census Bureau's Associate Director for Research and Methodology and Chief Scientist. He has been in the position since June 2016. The Research Methodology Directorate leads critical work to modernize operations and products, and he has been doing some very interesting work in leading the agency's effort to create a differentially private protection system for the 2020 census. And that is what he's going to tell us about today. Okay, with this, I'll hand it over to John.
Because it's easier to.
Good morning. It's a pleasure to be here. I want to thank Kamalika and Russ for the invitation. I can't help but call out that I don't think that this many economists have ever been in the same room to listen to me talk, so it's really a pleasure to be here and present today a little talk on how the Census Bureau is trying to be a good data steward in the 21st century. I need to remind you that I'm appearing in my official capacity, but my remarks represent my own opinion and not those of the US Census Bureau. Okay, I thought I would start off by showing the acknowledgement slide I usually present when I talk about the work that the Census Bureau has been doing to protect the confidentiality of the responses that we get from the 2020 Census of Population and Housing. That's its full title. I'll just say 2020 Census from now on. You will probably recognize some, but a distinct minority of the names on this list. I want to call out a few. First, I want to call out Dan Kiefer at Penn State, but who took his sabbatical year from 2016-17 at the Census Bureau, and he took the scientific lead in designing the system that I'm going to talk to you about today. And Simpson Garfinkel, the senior scientist for confidentiality and data access, who came over to the Census Bureau from NIST, where he was one of their cryptography and data security experts. He took responsibility for most of the engineering decisions that have been made. I won't read out the rest of the names. I will call out, in particular, though, Tammy Adams, who is a mathematical statistician. She designed the field operational control system for the 2020 census, where she became an expert in using Gurobi. She was on the team that produced many of the data products for the 2010 census, and so she was the metadata database that I needed to get the reconstruction tasks and analyses that I'm going to talk about today going. All right, so let's get started. Conducting a census of population is an extremely challenging job. It has two goals. We usually call them the dual mandate. The first goal is to collect the data that are necessary to underpin the democracy. I think many of you who are Americans, and possibly many of you who are not, know that the taking of a census of population is in Article 1, Section 1, Article 1, Section 2 of the US Constitution. I often wear a tie with that article on it, but I know that there's probably not a tie within 5 miles of here, so I didn't do that today. That says to conduct a population census within 3 years of the adoption of the Constitution and every 10 years thereafter, and then to use the results of that census to apportion the House of Representatives, to divide up the political power in the United States. So that's the mandate, to produce data that are fit for use. The statute that enables that mandate, Title 13 of the US Code, Section 9, requires that we protect the privacy of the individual data. That's a statutory obligation, but it's also necessary to ensure the trust of the residents of the United States who respond to the census, and to prevent abuse by others of the data that we collect. To give you some idea of just how big a job conducting a census of population is, the 2020 census has a life cycle cost estimate of $15.6 billion. For some tech companies, that's not necessarily a large number, but that is the largest peacetime undertaking of in a single activity of the US government, so it is actually a large number by governmental standards. It has to conduct what we call an address-based enumeration of the resident population with a reference date of April 1st, 2020. It's address-based because the critical factor is geolocating the respondents to the census to a physical location so they can be put, first of all, in the correct state for apportionment, and then in the correct voting district when all of the legislative districts in the United States are redrawn using the first data product that's released from the 2020 census. The field operations, many other operations have already begun, but the field operations begin in earnest this summer when we do the address canvassing. In 2010 and in previous censuses, that address canvassing operation involved sending an enumerator to every physical address in the United States known to the Census Bureau as of the summer before the census and getting it confirmed. We did most of that work in office over the last decade, and so these field enumerators will go to substantially less than 100% of the addresses, something on the order of 30% of the addresses, but they'll start working this summer, and we're already in the process of onboarding them. What are known as the peak operations, the activity of the census that you will see, begin with the self-response period, which the invitation letter goes out in March. The self-response date is targeted to April 1st of 2020. And then what's called the non-response follow-up, which typically begins about 6 weeks after Census Day and continues until the director of the Census Bureau, in consultation with many operational people, decides to end it, usually sometime near the end of August. All right. The peak data processing begins when the Internet self-response instrument is turned on, and the peak data analysis begins when the field operations close in September. So these are the basic steps. I should point out that I didn't put it on the slide, but the advertising campaign, the integrated communication campaign, has already begun, and the partnership program has already begun. So you'll begin seeing advertising and other content related to the 2020 census very soon. And here are the major data products. I've already mentioned the first one. By the 31st of December in 2020, we have to release to the Secretary of Commerce, who then delivers to the President of the United States, the apportionment of the House of Representatives. If you don't know the apportionment rules, they are conducted in the following manner. Every state gets at least one, and then the remainder are apportioned based on an algorithm known as the Hill-Huntington algorithm, which essentially minimizes the proportional deviations of the congressional districts. Shortly thereafter, and by statute before April 1st of 2021, we release a data product known by the very informative name of PL94-171 and referred to by the more informative name of the redistricting data, which is a very detailed file that is used by every state in the United States and the Department of Justice to draw all the electoral legislative districts in the country, not just the congressional ones. Any legislative body in the district has its districts redrawn on the basis of these data. And then in short order, we deliver a summary of the demographic and housing characteristics, a very detailed one, usually around the summer of the year after the census. And then detailed race and ethnicity data. We ask for the form, and I'll show you in a bit. And then detailed data on tribal affiliations for American Indians, Alaska Natives, and Native Hawaiians. In the 2010 census, this was more than 150 billion statistical tabulations. But the total data file was 15 gigabytes, and that includes fields that are never intended for publication. That was a lot of publications from what I think most of you would recognize as a relatively small amount of data by modern standards. So just to give you some idea, we intend to collect from each household essentially to confirm the address they were found at in our address database or collect the address of residence. And the definition of where you should respond is where you usually sleep or would have usually slept on April 1st, 2020. There's 6 pages of administrative regulations that define that, but I didn't bother to put those up here. We're going to get the total number of people living at that address, whether the housing unit is owned or rented, and then for each person living at that address, the person's name, the relationship to the adult person who's filling out the census form, we usually call that the householder or now person 1, birth date and age, sex at birth, Hispanic ethnicity, defined according to the 1997 OMB regulations, but now allowing a write-in for specific origins, and race, defined according to the same 1997 Office of Management and Budget categories, but allowing for each category detailed write-ins with more specifics. And finally, citizenship, although that question is currently enjoined pending Supreme Court review. We estimate there'll be 140 million addresses, 126 million occupied housing units, and 330 million people covered by the 2020 census. So I did a back-of-the-envelope calculation, and that's roughly 100 gigabytes of data. Very generous. That's actually 4 times my estimate, so I upped it quite a bit. Just to put that in context, because this is a truly big data conference, that's less than 1% of the worldwide mobile data use per second, according to the latest Cisco estimates. So basically, we're going to spend $15.6 billion and collect a quantity of data that most of your companies would miss if they blinked while they were scooping in the data that comes into the large tech company inputs. So it might seem like the Census Bureau's data stewardship problem is very different from the one at Amazon, Apple, Facebook, Google, Microsoft, Netflix, ... But those appearances can be deceiving. We all face the same fundamental law of information recovery, although I tend to refer to this as the database reconstruction theorem or the database reconstruction vulnerability. And we can all learn the same lessons from the cryptographers who took on the problem of how to publish statistics safely from confidential databases. You can't publish too many statistics. Noise infusion is necessary, not optional, necessary to meet most reasonable definitions of privacy protection. And Transparency about the methods is a benefit. Being able to say exactly what you did to protect the confidentiality of the data is a benefit. It allows the users of the data to understand how they should treat the statistics that you release, and it allows the providers of the data to independently verify that the confidentiality protection algorithms worked. One of the, if you look at our code base, which I'll show you where to find at the end of this talk, one of the things that goes in there is a fairly obscure-looking calculation that you wouldn't have any idea why it was stuck in the code. It's stuck in the code because with a very, 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 very high probability, if it's not equal to 0, the algorithms were actually run. Okay. When I started in this job in June of 2016, I began a project to discover whether or not the way that the Census Bureau had traditionally protected the confidentiality of its publications was vulnerable to a database reconstruction attack and then to a reconstruction-embedded re-identification attack. So what we did gradually over the course of about 18 months was, using only the published data from the 2010 census, we reconstructed records for all 308,745,538 people that were enumerated in the 2010 census. That's the official population from April 1st of 2010. We then took those reconstructed records and we used non-probabilistic record linkage. We joined them to commercial databases that we had acquired around the 2010 census to add personally identifiable information, names and addresses, to the reconstructed census records. If we were able to do that successfully, we called that a putative re-identification. That means that someone else attempting this would claim that this record is associated with this person. We then compared the putative re-identifications to the official gold standard confidential data inside the census firewall. When we could successfully link the putative re-identifications to the confidential data, we called that a confirmed re-identification. The data linkage experts in the audience might call that fourth bullet recall and that fifth bullet sensitivity. We called it a confirmed re-identification because it means that we were able to establish that that claim was correct. The harm from this attack is that the attacker would learn the actual self-response on race and ethnicity, which was not contained in any of those commercial databases. So it had features to the commercial databases that were not otherwise obtainable. Here's what we found. First of all, because of the publication standards that were used on the 2010 census, you can always reconstruct the census block, which is the 15-digit identifier that identifies which of the 11 million blocks in the United States that person lived at, and whether the person was of voting age exactly. So the records are right, and they're right in all 6,207,027 blocks in the 2010 census that contained any people at all. Next, we took the block, the sex, the age in years, all 63 OMB race categories, and ethnicity, reconstructed them, and compared the 308 million plus records to the gold standard confidential data on just those tabulation variables. No PII yet. They matched exactly, bit for bit, on 46% of the population. That's 142 million of the 308 million plus. Allowing the age to vary by plus or minus 1 year, they matched for 71% of the population, or for 219 million. That doesn't say anything about whether I could say what person that is. What it says is that those reconstructed data were a highly reliable image of the tabulation variables in the confidential data. That's salient because in the confidential data, on those variables, more than half of the population is unique, meaning there's no other record in the database that has the same values for those 5 variables. We used only the block, sex, and age to link to the commercial data. There we got a putative re-identification rate of 45% of the population, meaning we were able to attach a name and address to 138 million of the 308 million plus records. We then compared all the fields, name, block, sex, age, race, and ethnicity, directly to the confidential data. It's a confirmed re-identification if all of those fields match except for age, which was allowed to vary by plus or minus 1. We successfully confirmed the re-identification of 38% of the putatives, or 52 million people. That's 17% of the population. For the confirmed re-identifications, race and ethnicity are learned correctly, although the attacker will still have some uncertainty because the attacker doesn't have the census confidential data to confirm the re-identification with. This research establishes that the vulnerability identified by Irit Diner and Kobe Nassim in their famous 2003 article on database reconstruction is not a risk, it's an issue. That a risk is defined as something that has a probability less than 1, and an issue is defined as something that has a probability 1. The publication methods are vulnerable to reconstruction attacks. Now that might seem like a pretty specific example, but I'm pretty sure that just about everybody in this room knows a few things. They know that if you start harvesting data and you don't know whether they apply to the same entity, that you can reliably use record linkage techniques, or more generally, entity resolution techniques, to say that collections of features that aren't on the same record all belong to the same entity. Entity resolution is a big business, and there are probably more experts in this room on it than there are in most of the statistical agencies around the world combined. You also know that machine learning classifiers, AI, take these amplified entity records and build extremely reliable classifiers, recommenders, demand management systems. And I'm pretty sure everybody in this room knows that all of that is much harder with provable privacy guarantees for the entities. So that's where I think we have a lot of common ground. We're trying to engineer a solution to a vulnerability that if you publish too many statistics too accurately, no one in the input database can be given any reasonable assurance of the confidentiality of their input data. The same solutions don't apply to publications like the census publications or AI engines, but the same principles do, and the engineering challenges, I think, can be shared across statistical agencies and the tech industry. So, the Census Bureau's 150 billion tabulations from 15 gigabytes of data and tech industry's data integration and deep learning AI systems are both subject to an economic problem, the fundamental economic problem that is inherent in privacy protection, and that's what I'm going to spend the rest of the talk on today. You didn't think you were going to get out of here without a little economics, did you? All right. I don't think I'm alone in noting that one of the hardest lessons in modern data science is to accept that the fundamental law of information recovery imposes a resource constraint on data publication. That resource constraint is the death knell for traditional methods of publication from confidential data, and not just for statistical agencies. This is inherently an economic problem because there is a finite amount of information in any confidential database. And you can spend it two ways. You can create statistics, a classifier, a recommendation system, a demand management system. Those are all statistics because they expose characteristics of the database to the user, just like how many people of non-Hispanic white origin live in this block is a statistic. It exposes characteristics of the database to the users. You can either do that, or you can provide provable confidentiality protections, provable privacy protections to the entities that contributed to those data. And you can't do all of one and have any of the other. And I like to represent this on something that economists call a production possibilities frontier. If you're a statistician, you might also recognize it as a receiver operating characteristics curve. On the horizontal axis, you plot the privacy loss. We're going to be talking about differentially private systems here. And so the privacy loss is that privacy loss parameter epsilon that governs the global disclosure risk associated with a data set that's being protected by differential privacy. The vertical axis is a particular form of the accuracy measure. Accuracy is in the eyes of the beholder, and so there's no one accuracy measure for any particular data product. There can be many. I'm going to illustrate the accuracy measures that we're using to calibrate the redistricting application, but they all have the same feature. It's being measured as 100% accurate when the answer is identical to the answer you would get if there were no confidentiality protections, no privacy protections at all in the data publication system. So if you just tabulated the raw data, or you just built the recommender system from inputs that hadn't been protected by any kind of privacy filters, then 100% accuracy is the answer you get when you use those inputs. So it's a proper asymptote here. You can never be more than 100% accurate in that sense. You can never do better than an unfettered access to the data would allow. The 0-0 point is no accuracy. As the cryptographers have shown us, if you apply proper cryptographic definitions, if you insist on full semantic security, then the statistics are themselves a full encryption of the database, and they can't possibly have any accuracy. So those 2 points, labeled no accuracy and no privacy, I've deliberately not given you a scale on the horizontal axis because it depends on how you set your engineering up. But those 2 things are the extreme. In the middle, that thing is the production possibilities frontier. That's the best accuracy that you can achieve with the indicated privacy loss. And that's a global accuracy measure, or sorry, a global privacy loss measure. That's the epsilon from differential privacy. Takes account of all publications that are summarized in the accuracy measure. First lesson from economics, it's inefficient to operate below the frontier. If you operate below the frontier, you're giving up something that you can get for free. You're either using more privacy protection than you need for the given amount of accuracy, or you're surrendering accuracy because you poorly implemented your privacy protection system. That's lesson 1. In economics, that's called X inefficiency. But the other lesson, and the one that's the hardest to internalize, is it's infeasible to operate above the frontier. You would like to get to the 0-100% point. I won't even try. Yes, here. You'd like to get to the 0-100% point, but that's infeasible. All right? In economic terms, your preferences say that you're better going in the northwest direction, but the preferences are constrained by that production possibility frontier as to how close they can get to the 0-100% point. The third lesson from economics, and one that's most familiar, I suspect, to the people in this audience, is that research can move that frontier out. Better designed algorithms can deliver more accuracy for a given privacy loss. So the production possibility frontier, the blue line in the graphs I've just been showing you, is not a constant. It's a constantly improving way to publish data with provable privacy protections. In economics, that's called technological change, and technological change is happening in this industry at a prodigiously rapid rate. So those are the fundamentals. This is a hard problem because the publishers of data, so in my building, that's the statisticians and demographers who prepared those 150 billion tabulations from the 2010 census. In your buildings, that's the designers of those classifiers, recommender systems, demand management systems. They're used to thinking that they can have all the accuracy they want, just get more data. And that's never true. 100% accuracy is associated with no privacy protections. Right? But when they ask you, the computer science tech wizards, well, which point on this privacy loss accuracy frontier should I aim for? There's a really, really good reason why either you should say, I can't tell you, or they should say, I don't believe you when you answer. It's because it is fundamentally a social choice which of these 2 points, this one with high privacy protection and low accuracy, or this one with low privacy protection and high accuracy, which of those 2 points is better? No algorithm in the entire 40,000 plus papers published on differential privacy to date, no algorithm has an answer to that question. Algorithms labeled optimal are what economists call X-efficient. That means they give you a point on the production possibility frontier for a given epsilon. They're not optimal in the economic sense because optimality in the economic sense means that you've traded off the social benefits from better accuracy against the social costs of worse privacy protection. And there's nothing in the computer science to help with that problem. That requires a social welfare function. It requires a description of the preferences of the population that enabled the statistics. So in this case, description of the preferences of the population of the United States about their trade-offs for privacy versus accuracy. And I don't think it's any secret that that population is monumentally heterogeneous in their preferences. But that dual mandate I showed you on the first slide, that dual mandate says that somebody has to choose. And at the moment, that somebody is the Data Stewardship Executive Policy Committee of the US Census Bureau, because that's who the statute enabled. So how did that work? Well, we confronted this economic problem. We implemented a formal privacy guarantee for the 2020 census that relies on a core of differentially private subroutines, and they assign the technology tuning, building that frontier, to the 2020 disclosure avoidance team, specifically told not to engineer any hard choices into the algorithms. They're all controlled by knobs. And then the Data Stewardship Executive Policy Committee, that's essentially all the associate directors of the Census Bureau and the deputy director, set the parameters. So how does that work? Well, to be fit for their intended uses, we have to subject the entire publication system to a privacy loss budget. So every person inside the Census Bureau's headquarters and all of its user communities in the redistricting area and the demographic area around the country, all of their uses have to be identified and codified and summarized in some formal fitness for use accuracy statistics. To design the prototype system that was used for the 2018 end-to-end census test, we did this for redistricting applications. We now have to face many of the person and household level tables in the demographic and housing characteristics, and we've done that too. But there are still 100 billion queries that we have to figure out how to summarize in a reasonable way, including suppression, but that's probably not the answer that most people are expecting. It'll be a question of how accurate those queries are or can be. We've developed methods for quantifying and displaying the system-wide trade-offs between the accuracy of the decennial census data products and the privacy loss budget assigned to the complete set of tabulations. Considering that that work began in mid-2016, that no organization anywhere in the world has developed a full central differential privacy system and deployed it, it's already a monumental achievement. I'm going to show you some actual data computed off the 2010 census used in determining how to set the privacy loss budget for the 2018 end-to-end census. So these are not hypothetical figures anymore. These are real figures. The x-axis is the actual privacy loss parameter, epsilon, for the entire system. All the tables summarized in this figure. So what are the tables summarized in this figure? The blue line is the block level redistricting tabulations. So for every block in the state of Rhode Island, it's the voting age population and the non-voting age population broken down by 126 different race and ethnicity categories as specified by the 1997 Office of Management and Budget Guidelines. A table for every block. Those tables aggregate to the orange line, that might be red in some of your eyes, which is the next one up, which is the tract level summary. So the typical block has about 30 people in it if it's inhabited. The typical tract has about 4,000 people in it if it's inhabited. The next two lines, the green and the yellow line, are coincident because the data are similarly accurate at both the county, there are only 5 counties in Rhode Island, and the state level, there's only 1 state in Rhode Island. So these represent the actual efficiency of the algorithms used to do the 2018 test products as they would be fit from the 2010 data. So this is the result of simulations that use those data as input. Right. The debate occurred on November 8th of 2018 inside the Data Stewardship Executive Policy Committee. I was in New York City doing other duties as assigned, so I came in by video. The Data Stewardship Executive Policy Committee, for the end-to-end test, chose the block level epsilon, chose the block level point where epsilon is 0.25 and accuracy is 0.64, which means that the blocks, which are the pixels used to build the legislative districts, have those properties. There is no legislative district in the country that is a single block. Those blocks are used to build geographic areas with increasingly larger populations as the size of the population represented in the particular legislature increases. And so what's salient is that even at that same epsilon, remember this epsilon isn't separately applied to each of the geographic levels. The epsilon is shared across all the geographic levels. It's a global privacy loss budget allocated according to the top-down algorithms, I'll show you the reference for that too, that were designed into the 2020 disclosure avoidance system. Well, for a tract, which remember has about 4,000 people in it on average, the accuracy is 98%. And for counties and the state, the accuracy is essentially 100%. The system has the property that as the population in the geographic area being summarized increases, the accuracy increases. This accuracy metric is one that was selected for the redistricting application. It's basically 1 minus the average total variation distance in all of the tables produced at that geographic level. That said, the 2018 end-to-end census test products are test products. They're not going to be used to draw any legislative districts anywhere in the state of Rhode Island or any place else. Consequently, the DSEP thought that it would be best to err on the side of heightened privacy protection rather than heightened accuracy in this test, because first of all, it might turn out that epsilon of 0.25 is perfectly adequate for the redistricting application. It might well be. But secondly, nobody's going to do any redistricting with these data. They're just going to load them into their computer programs and make sure they're formatted correctly. So there was no good case for increasing the accuracy. That's not the case for the subsequent decisions. There's an excellent case for increasing the accuracy. And this chart is just the tip of the iceberg. In the demographic profiles, the sex and age data of each block and tract need to be summarized, and they need to be summarized by race and ethnicity. In the detailed race and ethnicity tables, someplace between 400 and 800 detail codes, they don't exist yet because the people haven't written in their answers yet, but that's the range of values we expect, have to be summarized in a way that allows representatives of those different interest groups to identify how many of them they are and what some of their demographic properties are. For the American Indian, Alaska Native, and Native Hawaiian tribal areas, the census is their only access to data on the counts of those populations until the next census, because the American Community Survey has inadequate sample size to tabulate most of them. So it's important to understand that redistricting, demography, race, ethnicity, and the one I haven't mentioned, those all have use cases where the defenders of those use cases make a pretty coherent argument for high accuracy. But living out here might not be a realistic option, because living out there, the relative promises that differential privacy guarantees do not translate into nearly as strong a confidentiality protection as when you live over here. That's a really, really hard social choice problem. And we need to work hard and use more psychological, sociological, demographic, and economic tools, as well as some computer science, to try to solve it. I think internet giants are struggling to deal with the same choice. I think their privacy engineers tell them that they can get reasonable accuracy. In fact, I saw a presentation last week that suggested epsilons in the same range we're considering if the Census Bureau can deliver decent AI. But I'm guessing, you can confirm during the Q&A period, I'm just about done, I'm guessing that when you sit around the conference tables in your companies, the privacy engineers have on one side of the table the arguments for how to get decent privacy protection, and the accuracy engineers have on their side of the table all of the cost-benefit analysis associated with removing 1% of uncertainty in a classifier. It's not any easier choice for your companies than it is for my employer. But just because it's not an easy choice doesn't mean it will go away. You can make some of these choices implicitly, and if you do, this picture is almost surely going to come back to comment on your choices. So science and policy have to address a lot of questions. For the 2020 census, we need a policy that says what the privacy loss budget should be for all of the uses of the 2020 census. We need to discuss how the Census Bureau should handle management-imposed accuracy requirements. For example, we are releasing the populations of the 50 states without privacy protections. If you do your math, that is a violation of differential privacy. It's one mandated by the Data Stewardship Executive Policy Committee, and we will be commenting on the implications for the privacy guarantees in the presence of those management-imposed accuracy requirements. Then we have to decide how to allocate that privacy loss budget over the next 7 decades, 72 years from the census it's officially released to the public, which is why you can use the 1940 census right now, and I'll show you how you might want to do that in a second. Can the Census Bureau insist that researchers present their differentially private analysis programs as a part of the project review process? If we did, at the moment we would have no projects to review because most of the analysts don't know how to do that. But even if we did, where would the experts to assess those proposals and certify the implementations come from? That's not a skill set that has yet been developed inside statistical agencies. And I might be speaking out of school here, but I suspect that statistical agencies amongst the representatives in this room are not the only businesses that don't have that skill set handy. So if you want more background on the 2020 Census Disclosure Avoidance System, the design is discussed in front of the committee, the Census Scientific Advisory Committee in the 2017 presentation. Last year, my KDD talk talked about the difference between the top-down and the block-by-block algorithms. We have a 2018 WPES paper that talks about the implementation issues, a recent ACMQ paper that talks about database reconstruction in general, The 2018 CSAC presentation shows how they were implemented for the 2018 end-to-end test. And we released a blog last Thursday that shows you how to access the public code base. We put the code base in the public domain that we used for the 18 test, and then how to load the 1940 census curated by IPMS into that code base and do your own experiments with our software. I look forward to the Q&A session. Thank you very much.
Hi.
He rose first. Go ahead. Say your name and affiliation, please.
Hi, my name's Brian Milch. I work at Google. I'm wondering how you've worked on translating these epsilons, which are these abstract numbers in the differential privacy theory, into something like how much somebody can figure out your race, or some kinds of questions you can really get your hands on in thinking about potential harms.
Okay, so thank you for that question. The first thing I'd like to refer you to is my 2019 American Economic Review article with Ian Schmuddy. It appeared in the January edition. It's also on Archive. It's the same version on Archive, so if you don't remember and you can't get past the paywall, you can see it there, where we showed how to interpret the epsilon and then how to translate it into something that you could put in a social welfare function to make decisions about. And then a very recent paper in the American Economic Association Papers and Proceedings, it should not be firewalled. Ian Schmuddy, Lars Vilhuber, William Sexton, and I showed how to translate the differential privacy epsilon into the kind of re-identification guarantee that the people I work with can interpret. So, as I think most people know, formal privacy systems give you a relative guarantee. They don't make many assumptions about the attacker's priors. What they do is they produce guarantees on how much those priors are improved as a consequence of the statistical publications. So we showed that the system, similar to the one used in the 18 test, could be interpreted as not improving the prior of re-identifying a specific attribute and associating it with a specific person by more than e to the 2 epsilon. Does that help?
Yeah, thank you very much.
You're welcome.
Hi, Tom Dieter from Amazon. So thank you very much, really fascinating talk. I was interested in the record linkage attacks that you mentioned, and whether you've looked at what happens as you increase your epsilon on the performance of those record linkage attacks, and whether you've considered using that as an extra tool to help you when choosing an epsilon.
Thanks very much for that question. So we're continuing to do experiments with those reconstruction and re-identification attacks, and as we speak, the code base is running on what for the Census Bureau is a large set of servers, trying to determine how long it takes to do full country reconstructions from the approximately 6 billion tabulations that we used as input to that. We're also continuing to run sensitivity experiments to show how unique the reconstruction is. We know the reconstruction isn't unique, but we also know that the block and the voting age variable are always identical in all the reconstructions. It turns out that most of the variables are identical in most of the reconstructions, and there's a small amount of variation in the race and ethnicity and a larger amount of variation in the age. And so one of the key features of the disclosure protection system for the 2020 census is that it protects the geospatial location, so those block reconstructions are no longer exactly accurate. We will eventually run the experiments that you asked for, but we're not ready to talk about them yet. Thanks.
Hey.
Blue shirt.
This is Yuxiang Wang from UC Santa Barbara. Thanks for the wonderful talk, and I really enjoyed the part of the talk where you talk about the social choices associated with choosing the accuracy and privacy trade-off. So my question is about the privacy model that's running by US Census and what's the differences between the choices that has been adopted by tech industry. Because in the deployment of Google and Apple, they've been working with the local differential privacy model where individuals, when they submit their data, they actually perturb their own data to prevent privacy leakage even to the data collectors themselves. Can you comment on that model and what's the differences between this and the model that's adopted and endorsed by the Census Bureau?
Thank you very much for that question. That was the subject of my KDD talk last summer, so if you play that video, you can see it. And it was also discussed in the Census Scientific Advisory Committee meeting, the December 2018 one. So that's why I showed you the statistics on how much data are actually collected in a census. Let's call it 100 gigabytes, less than 1 second's traffic in this mobile network. The local DP model, the closest approximation to it that we could implement would be with the privacy protections applied at the block level, the lowest level of geography that we get. Or in principle, we could apply them at the address level. It would give the same result. If you build all the tabular summaries using that privacy protection system, they do not have the property that as the population in the geographic area increases, the accuracy of the statistic increases. That's a critical failing of that way of doing the privacy protection because we can't wait 3 decades to get another billion observations if we don't have enough observations to do the redistricting on April 1st of 2021. So a central model is the only viable one, and in a central model, you have to manage the application of the privacy loss budget to all of the table sets. I showed you the hierarchical management for geography. We're doing similar things on other dimensions of the table, but we're not ready to talk about them in public yet. That's why we didn't use the local DP model.
Thank you.
I think you were next. I might be wrong. Oh, okay, go ahead.
Is it working? Yeah, good. Hello, thanks for your talk. I'm Karl-Johann Simon Gabriel from the Max Planck Institute for Intelligent Systems in Germany. I'm not an expert, so please forgive my ignorance if this question is stupid. But I was wondering, is the reconstruction probability homogeneous across the population? Because I could imagine, for example, that for some parts of the population, reconstruction would work very well, and for others not. I don't know, for example, if you live in Alaska, it's more easy to identify you than if you live in Los Angeles.
Thank you for that question. By agreement with our own Data Stewardship Executive Policy Committee, we have so far only released the high-level summaries from that reconstruction attack. But I can tell you that we are preparing a scientific paper. It will be exposed to full peer review. There aren't any good predictors of when the reconstruction attack would be successful. And in particular, the block population, which you might have thought would be a predictor, does not appear to be. We haven't finished the analysis, but does not appear to be a good predictor. Nor does the homophily index for the block, namely how homogeneous are the people in that block on certain characteristics. So at the moment, it does appear that whether that attack is successful is relatively random as a function of characteristics in the population. That's all I can talk about at this point on the specifics of those statistics.
Thanks.
Hi, Ethan Dyer, Google. Sort of a related question. So I was curious if you guys think about redesigning blocks with privacy in mind. Is that something that's possible?
So yes, that is something that's possible. Thank you for that question. That is something that's possible. I didn't go deeply into the politics isn't the right word, the regulatory environment underlying the block definitions, but the publication of the redistricting data is the only statutorily mandated product from a census. And the geography at which it is published is subject to negotiation between the Census Bureau and the National Conference for State Legislatures. And those negotiations take place over the course of the decade, and they're confirmed in Federal Register notices that specify first the general substance and then the specific form of those products. So at this point in the decade, they can't be redesigned, but that's a really reasonable looking forward recommendation. Thank you.
Thanks, John. Another question from Yuxiang Wang from UC Santa Barbara. So the question is regarding designing a good accuracy measure that covers every individual in the population. For instance, if differential privacy introduces error, and does that error hurt the state of California and the state of Iowa in the same way? What's the implication of the different accuracy metric in the social choices?
So I've only shown you, thank you for that question. I've only shown you accuracy measures that we developed for redistricting data. We're currently working with the voting rights section at the Department of Justice and with demographers to develop other accuracy measures. The question is whether they are fit for use, and the fitness for use means that you have some idea that they perform properly in some hopefully very large percentage of the applications. We use a fitness for use measure on the American Community Survey 1-year tabulations that says if the table doesn't have a median coefficient of variation less than 0.61, the whole table is suppressed, and that has nothing to do with privacy protection. It has to do with accuracy. We don't consider those data fit for use. So we're trying to develop metrics like that. And then with metrics like that, you can assess whether there are some parts of the country that wouldn't get as much data, and that would, of course, be a concern that would have to be addressed. Thanks again.
How about the...
There's a bunch of other people who want to ask some questions. Okay. I thought I'd give them a chance, okay? Thank you.
Hi, I'm Chris with the Department of Defense. I'm curious how the reconstruction probabilities and accuracies that you get compared to what you might get with publicly available demographic data. Say, the simplest example would be guessing everybody is Caucasian.
Thank you for that question. We haven't completed those experiments yet. That is something that our internal reviewers have asked to see, so I don't have a good answer. That's a reasonable question.
Hello, my name is Doron from the Technion in Israel. I would imagine that some features are more, I would be concerned from some features to be more private than others. Do you take that into account when you define your differential privacy?
So by statute, all features are equally sensitive in statistical agency publications. And so we are, that's one of the few statutory prohibitions.
Okay.
Fitness for use, on the other hand, says that the accuracy doesn't have a comparable requirement. So we are considering the use cases for the different tables separately. Hope that helps.
Okay, thank you.
I think that had to be the last question, right? Okay. All right, so thank you all very much. I really enjoyed this.
So we're now going to have our first Best Paper Award, Challenging Common Assumptions in Unsupervised Learning of Disentangled Representations. And congratulations to the team. So we're just going to give out these certificates. Congratulations.
Thank you.
Awesome. So let's see.
Hi everyone, my name is Oliver Bochem. I'm a research scientist in the Google Brain team in Zurich, and I'm really excited to present our paper, Challenging Common Assumptions in the Unsupervised Learning of Disentangled Representations. This is joint work with Francesco Locatello, Stefan Bauer, Mario Lucic, Gunnar Raj, Sylvain Shelley, and Bernhard Schurkopf. Let's start with some basics. In representation learning, we're often given access to high-dimensional observations, such as this pretty image of Switzerland here. Now, our goal in representation learning is to learn a function which takes as input such an image and returns a vector or representation that captures the content of that image and is hopefully useful for many different downstream tasks. Now, a common assumption that people make when doing representation learning is that these observations are not truly high-dimensional, but that they are a manifestation of the real world, which is supposed to be, or which is assumed to be, lower dimensional. In particular, one often assumes that the image, such as this one here, is a manifestation of a lower dimensional set of independent ground truth factors of variation. So for example, in this image, this could be different objects, such as the houses, the sheep, the trees, and these objects, they have properties such as shape, position, and size. Now, there are many different things that one might want to have in a representation, and one idea that has gained quite a lot of traction in the last few years is that of disentanglement. Now, what is disentanglement? Well, there is no single commonly accepted formalization of disentanglement, but there is one idea that has been used over and over again in the last few years, and it's that different ground truth factors of variations should be captured in different parts of the representation, which means that if we change a single factor of variation, this should lead to a single change in representation. Now, if that sounds confusing, that's okay, because I'm going to illustrate it with a visual example. So here, what we see is a data set used in the disentanglement literature called Shapes3D. And on each of these panels, we show what happens if we change one of the ground truth generative factors. For example, on top left, we show what happens if we change the floor color, which is one factor, on the top right, the object color, on the bottom left, the object size. Now, let me show you what a disentangled representation looks like. So for example, here on the left, what we show is, we show again a whole bunch of these small animations, and what these animations, they are what's called a latent space traversal in one of these underlying in one of these underlying models. And what they capture is they essentially visualize what is captured in the different coordinates of a representation. So here this is a 10-dimensional representation, so each of these panels corresponds to one of the coordinates. And now you can see disentanglement here is kind of defined that as each of these coordinates captures information with regards to one of the factors of variations, or none at all, which is also fine because there's more dimensions in representation than there are actual ground truth factors. On the other hand, we have this entangled representation here on the right-hand side, where you can see that, for example, in the middle on the top, we see that this dimension of the representation would capture different ground truth factors such as object shape, background wall color, floor color, and so on. Now, in this paper, we look at a problem which is called the unsupervised learning of disentangled representations. And this has gained quite a lot of traction in the last few years with many different methods being proposed. And the idea is we get many of these images, and we have to learn a representation, but we do not observe, or we don't have access to the labels, or we don't have access to labels of the ground truth factors of variation. Now, the key contributions of these papers are twofold. First, we have a theoretical result which shows that for arbitrary data, the unsupervised learning of disentangled representations is impossible. And now this is actually in contrast, this is a pretty fundamental thing in the sense that it's in contrast to supervised learning, which in that it means that even if you have an infinite number of data, the problem can be impossible. Now this is at odds with, or this may seem at odds with what people have observed in the last few years when they've trained many of these models, where they've seen, okay, suddenly we get pretty visualizations such as the one on the, like 2 slides ago, where we actually see disentanglement happening in models that we have trained fully unsupervised. So what we kind of wanted to do is, okay, let's try to reconcile this. One potential explanation is that these theoretical results, this one is essentially a worst case result, which means that it's kind of, in the worst case, there's a data set where it's impossible. And maybe real world data, or at least the data sets used in the literature, they have some structure that we can exploit using inductive biases in our methods. So for this reason, we set up a large-scale empirical study where the goal was to investigate whether we can learn disentangled representations in a purely unsupervised way. This means without ever looking at the labels. To do this, we set up a large-scale study. We implemented 6 different state-of-the-art disentanglement methods. We collected 7 data sets. We coded up 6 different metrics used to measure disentanglement. We then combined all the methods with the data sets. We took every combination. We defined hyperparameter sweeps for each of the methods. We set up a bunch of random seeds, and we ran, we trained all these models. Then we took all these models, we computed all the scores, giving us a total of more than 10,000 trained models and more than 150,000 disentanglement scores. Well, there are many different results in this paper, but I'm going to focus on basically answering 3 different questions, which should give an answer to our main question: can we learn disentangled representations in a purely unsupervised way? Now, essentially, we try to look at this problem. Let's suppose we are a practitioner, we're given a new data set, and we want to learn a disentangled representation. Well, what are the questions that we need an answer to? Well, the first one is, which of all these methods should we actually be implementing and then using? Second, as we have a method, we have to go and choose some hyperparameters, because most of these methods, or all of these methods that we considered, have a hyperparameter that we need to set. Lastly, you're probably not going to just train a single model, but a whole bunch of models. And after training, we have to have a way to select which ones of the models we actually should use. So after we ran all these experiments, we looked at the data, we looked at all the combinations of data sets, disentanglement scores, methods, and what became pretty clear very quickly was that the choice of the objective function that you use doesn't really seem to matter this much. What I'm showing here on this plot is on the x-axis we have different models. This is on a specific data set and for this specific score, but the big picture looks the same. So in the x-axis we have the different methods, different objective functions. On the y-axis we plot the distribution over scores as hyperparameters and the random seeds of the specific methods are varied. What we can see is that this is heavily overlapping, indicating that the random seed and the hyperparameters seem to matter much more than the actual objective function. Now, while this doesn't give us an answer which method is the best, it seems that this question doesn't really matter, and we maybe should focus on more on question 2 and question 3. So how could we go about choosing hyperparameters? Well, again, we looked at all the combinations of metrics, data sets, methods, and we tried to derive simple recipes for actually choosing these hyperparameters. For example, all these methods have a regularization term that should encourage disentanglement, so maybe if we increase the strength of that term, that will lead to more disentanglement. Now, after slicing and dicing this data, we concluded with, okay, we cannot identify any obvious trends that is consistent across all data sets and can be used as a rule of thumb. And it's very interesting here is that, okay, if you look at like single or 1 or 2 data sets, you may see some trends. If you look at more of them, it suddenly may not happen, or you may see the exact opposite. So we thought, well, maybe this is too hard, maybe let's try something else. Suppose you're given a new data set, but where you don't have the ground truth factors of variation, but maybe you have a similar data set where you actually do. So what we tried is, well, what happens if we go to one data set, we look at how well different models do, or different hyperparameters do, we choose these hyperparameters, transfer them to a different data set, and see how well we do there. Now in this plot here, what we are showing is, we show the Spearman rank correlation of the average performance of different hyperparameter settings across different data sets for one of the metrics. Now what we see is that this transfer strategy seems to work to some degree, in particular if the data sets are very similar. However, it's not perfect. Now this kind of gives us an answer to the second question, right? There doesn't seem to be clear rules of thumbs, but at least with kind of transfer, this might be actually working. But this doesn't help us with the third question, which is how to select a best model from a set of trained models. Because the results before that I showed, they only applied to the actual mean, what happens kind of on average, not what happens if we train a single model. So now, okay, for this third question, how do we select kind of the best model? Like the simplest strategy we could do is we just take our prior transfer strategy and we take that setting and we train one single model on our new data set and we see how well this does. Well, we set up an experiment where we took this strategy, we took this model and compared it to a random model. What we found is, that with this transfer strategy, we only beat random model selection, and this is random model selection across all possible kind of settings, and there is maybe some of them which are pretty bad. The transfer strategy only beats the random model selection strategy 60% of the times. Now you might ask, why is this happening? Well, the culprit is that as you take a specific method and hyperparameter setting and you train many models with different random seeds, there's a large variance in between these different runs. And not only that, what you can also see here from this plot where we plot for one model and one metric, we show disentanglement scores where we vary the regularization strength of the model and on the x-axis, and we show the distribution of the scores achieved on the y-axis. We again see that the ranges achieved are heavily overlapping. And the implication is that good runs from bad hyperparameter settings can easily outperform bad runs from good hyperparameter settings. Now, basically, this means that we need a way that after we've trained a whole bunch of models, we need a way to select which model we should actually use. And remember, this is the unsupervised setting, so we're not allowed to use the disentanglement scores because they actually require labels to compute. So we thought, okay, well, when we train these models, we collect all these unsupervised training methods. Maybe they would be useful. Maybe if a model has a lower reconstruction error, then the model, the representation that we obtain out of this model will be more disentangled. Well, looking at, again, all these data sets, we couldn't find any evidence that this is actually the case. In particular, correlation seems to be pretty low between these scores or even kind of changing on different data sets. Now, what can we conclude for this for the question 3? Basically, what we conclude is that while we may train many models, and there is some models which have really good disentangled representations, it's very hard to find them. And at least in our opinion, this problem of finding these models remains still an open problem and should be investigated in further research. Now, in this paper, we have many more results. So let me just give you the kind of the key takeaways from the paper. Now, the first thing is what I essentially covered in this talk, and based on the theoretical impossibility result and the empirical study, we argued the role of inductive biases and supervision should be made much more explicit. It's very easy to it's very easy if you train models, you look at the scores, based on this, you select your hyperparameters, you go on. It's very easy to infuse supervision into your process, which might bias kind of the scientific insights you get. Similarly, the same thing can happen if you only look at very few data sets. In particular, this unsupervised model selection problem that we've just seen before persists as a key question. What we argue is that we might need to go beyond the pure unsupervised setting to a setting where we kind of relax our assumptions a bit and where we say we have access to a few labels, or we have access to a temporal component, or we can interact with the environment. Now, in this talk, I have also always assumed that these notions of disentanglement are actually a desirable property. Now, in the paper, we have some experiments where we investigate this based on a simple downstream task. And However, we couldn't find evidence that some of the assumptions people have about disentanglement is actually that they are actually confirmed. So what we argue is that concrete practical benefits of disentanglement should be demonstrated further. And lastly, I would like to, what became very clear when doing this study is that actually doing a sound, reproducible experimental setup with several data sets is crucial because, as I said before, if you only look at a single data set, you may see trends that are not there if you look at several. Now, to help researchers with this, we have released an open source library for research into disentangled representations. It contains all the methods, metrics, end-to-end training and visual and evaluation pipelines. It automatically generates these pretty animations, and I'm aware of more than 5 papers that have used this library so far. Also, we wanted to make it very easy for other researchers to reproduce the results. We kind of spent quite a lot of time on this, and basically with 5 commands, you can go download the code, install it, download the data, and reproduce models from this study. Now, running 10,000 models can be computationally prohibitive, so we decided, okay, maybe let's just also release more than 10,000 models. We hope this helps researchers first validate our results, and second, test out their own research ideas, such as, for example, evaluating a new disentanglement metric on these set of pre-trained models. Now, before I conclude, I wanted to point to some additional work which essentially tackles questions posted in this paper. We finished this study about 6 months ago. In the meantime, we've been busy looking at various of the follow-up questions posted in this work. We looked at what happens if we what happens if we have access to very few labels. Turns out model selection then can be done. Second, we looked at 2 potential motivations why you would want to have disentangled representations. We found that for non-trivial downstream tasks, there seems to be an argument for sample efficiency. We also saw in a different study that disentangled representations might be useful to make downstream predictions more fair. As a last point, we also built a large-scale, data set of real images for disentanglement research based on a robotic platform, and we are organizing a NeurIPS competition on learning disentangled representations, which is going to start in a few days. So if you're working on disentanglement, I heavily recommend you to check it out. If you have questions, I would be happy to take them now, or at our poster, which is 271 today. Thank you.
So we have a few minutes for questions. If you want to ask questions, I think.
Hello, I have a question on your paper. As far as I know, the graph that you show on the car 3D data set, maybe, it seems to that the effect of randomness is more important than the method because the data set is very easy on disentanglement task. I mean that, for example, in this prize, the scores is very different from many methods in average.
Yeah, so one of the key things we did when we set up this study was a lot of the research has been done on these sprite data sets that you mentioned. We have seen some other data set where we also have access to ground truth facts of variation, such as the cars 3D data set that you mentioned. And we actually also wanted to see because what happens if you actually go to a new data set, right? One which is not exactly the same as the one where all the research has done before. So the idea was, okay, most of the stuff was explored on these sprites, but let's actually see how well these methods do kind of on a different data set where much less work has been done. And that's why that's kind of, I don't know what exactly your question was, but that's why you see also differences in between the data sets. The whole point is if it's unsupervised, right? And like now we're talking about images where you may have some kind of human intuition where you can do visual inspection. What happens if you go to a data set where you don't know the ground truth factors of variation, right?
Thank you.
Ian, yeah?
Hey, thanks for the talk, Olivier. So on the data sets that you're using, I'm not, sorry, can you hear me okay?
Yeah?
Yeah, okay. It looked like, so these are all synthetic data sets, which makes sense. I think that they all have the property that the factors of variation are very uniformly. Have you been able to look at any data sets where the factors of variations are not uniformly varying? Like, there is a correlation between two factors, for example?
We didn't look at this. I guess it's kind of, this is the simplest setting, right? Like if you have independent factors of variations, this is kind of the ideal setting. So, and given that even in this setting it's very hard, I would imagine that most of these things wouldn't work in these settings either, but I think it's, I guess that's kind of, you first have to solve the independent case before you can go to the correlated case. That's what I would argue.
Sorry, so I guess my question is whether or not detecting factors of variation might be simpler where there are correlated factors of variations, which is, I think, more common in the real world. Do you have any thoughts on that?
I think the whole point of disentanglement research, so if you, for example, take this shapes 3 data set, right? If you take wall color and floor color, right? Like the key idea is that really this should be modeled independently, right? These are 2 different things in the world, so sure, if you have kind of, you might have correlations, but if you go to the real world between this exact thing, right? Like wall color and floor color, I think, yeah, if for example, if they're perfectly correlated, right, it's probably easier because you essentially only have one ground truth factor of variation.
Yeah. Great, thanks.
Yeah.
I have another.
Maybe you have one more question here?
Yes.
Yeah.
Thanks a lot for the very nice presentation. So you mentioned that transfer the data set could help. Could you describe the major factors when we select the data set to be transferred?
So I think currently the state of the field of disentanglement learning is on these, like what I would call toy-like data sets, right? I think there's still a lot of work to be done to go to real-world data sets. So one experiment that we did was we looked at these sprites and then different versions of these sprites, and then transfer, unsurprisingly, actually works better than if you go to other data sets. I think, yeah, I don't think this stuff is ready yet that you want to throw that stuff in the real world. Yeah.
Thank you.
One last question on the left. Yeah.
Yes. So you claim that it's impossible to learn disentangled representations.
Yes.
What is the precise, rigorous mathematical definition of disentangled, and what does it mean to be impossible?
So the full details are in the paper, and I skipped it here in the talk. The way we do this in the paper, and I think there's many ways of doing this. We did it in this way because it's the most simplest and I think the most accessible, is that we defined kind of going from the ground truth factors of variation to the representation as a function, and then kind of the derivative from going from the ground truth factors of variation to the actual representation should be kind of a one-to-one correspondence. Okay, that's the definition that we use, right? So you shouldn't, like, if you change one factor, it should only have a non-zero derivative at most one of the coordinates, right? And that's this. And now the proof, the way it works is we say essentially, as it's an unsupervised setting, you only observe the observations, the images, and then we construct 2 different generative models that could have generated the same observations. These are deterministic transformations in kind of the same probability space. And then we argue, well, if you learn the representation that is entangled to one of them, then it also needs to be, sorry, it is entangled to one of them, then it is entangled to the other one. Right? And so it's kind of a worst case one, and because you, in an unsupervised setting, you have no way of identifying which of the generative models is actually the true one, right? So that's why I said in a talk, there is hope if you have more structure, right? Because it might exclude some of these generative models. Thanks.
Okay, well, let's thank the speaker again. So just quick, we have a 30-minute break. All the sessions are going to start at 11 o'clock, so make sure you're there on time. And we're off. The best part of the conference now is the break. And you get to stand in long lines and try to get out of this room. So anyways, we'll start at 11 o'clock. Thank you.
What if the valley's too wide to hold your dreams? What if your heart is grown too dull to gleam? What if it's ancestral, it's running through your genes? It's all too much, now you're bursting at the seams.